think we're live now, hopefully. Hello everybody, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today I will be going over some commonly asked mathematics questions at both the high school and college levels. And if you need some homework help or some tutoring, check out the links in the description below. Cool, so let's get it moving on this mathematic magic. So the first question that we will be dealing with today is the integral of cos squared x. So I'll write down our little question here. Oops. I'll just make my pen a little thicker. So the integration of cos squared of x with respect to x. Now, typically when you see integration problems and you see stuff like cos squared and such, typically it's a good idea to think about our trigonomic identities, because they can definitely help give us an easier integral to solve, because this by itself is kind of tough. So one identity that I think could be useful is that cos squared of x is equal to, I think it's here, yep, it is 1 plus cos of 2x, I believe. Yep. Over 2. Cool. So if we try to take the integral of the cos squared x on this side, it is the same as taking the integral of this thing here. And in my opinion, taking the integral of what's on the right side of this equals is going to be a little bit easier to do than the left side. So let's rewrite our integral so that we're taking the integral of this instead of the integral of cos squared x. Okay, so we have the integral of 1 plus cos of 2 times x divided by 2 dx. Awesome. So given this, we know that we can actually split this into two terms. So we can divide, you see how the top is 1 plus cos 2x. We can rewrite this as the integral of 1 over 2 plus cos 2x over 2 dx. And actually, even easier, we can factor out the divide by 2, and we can pull that even outside of the integral. So that might be even easier. So it'd be 1/2, factoring out the 1/2 outside of the integral. So it'd be 1 plus cos of 2 times x dx. Okay, cool. We know that a nice rule with integrals is that if you are taking the integrals of something added with another thing, that is really the same as taking the integral of them individually and then adding them together. So we can further rewrite this as this is equal to 1/2 the integral of 1 dx plus 1/2 of the integral of cos 2x with respect to x. Okay, nice. Now, this should not feel as difficult as it did before when it was just cos squared of x. Okay, so let's do the first term, the integral of 1 with respect to x. So we know that the integral of 1 is simply x itself. And that makes perfect sense, because if we take x and we take the derivative of x, that should give us 1. So yeah, makes sense to me. Equals x plus, or 1/2 x. Don't forget that 1/2. If you forget those coefficients in the front, you're not going to get the question right. Cool, so let's do our second term. Our second term is 1/2 times the integral of cos 2 times x. So the integral of cos 2 times x is, well, let's think about it. We know the derivative of sine is going to be cos. And if we have like a function inside of the argument to sine, that means we will have to multiply the entire derivative with the derivative of the internal of the argument. So here, and then the argument is going to stay the same. So I'm actually going to draw this to this side. Like, we know that the derivative of sine 2x is going to be equal to 2 times sine x, or times 2 sine x. That's because, like, whoops, that should be cos, actually. I'll erase that real fast. And the reason we do that is because the chain rule. So because we have a composition of function, one function is like the function 2x is the argument passed to sine x. We need to take the internal derivative of that and multiply it out. But we don't have cos 2x. We have we don't have 2 times cos 2x. We just have cos 2x. So what if we I'll erase these and move them a little bit to the right. So if we had actually I'll rewrite this as, what if we were taking the derivative of What if we were taking the derivative of 1/2 d over dx? If we take the derivative of 1/2 sine 2x, that means when we take the derivative, the 2 that we have to multiply it with because of the chain rule, that is going to get neutralized with the 1/2 term, and our result is going to be 1/2 times 2, because that's the internal derivative, times cos 2x, which is just equal to cos 2x. That's because the 1/2 and the 2, they neutralize each other. So they just become multiplied by 1, and we don't really need to write that, because multiplying by 1, well, that's just multiplying by 1. All right, cool, that's beautiful. So we basically know that if you find something where the derivative of it is what you're looking for, that means we've basically found the integral. So we still need to keep this 1/2 term, this 1/2 term. So 1/2, and we found that our integral of cos 2x is just something that you would take the derivative of to get it. And we know that the derivative of 1/2 sine 2x would give us cos 2x. So within the bracket here, we're going to put 1/2 sine 2x. Okay, cool. That's great. Now we can just expand out, like we can multiply the 1/2 into here. So we'll get 1/2 x plus 1/4. So the denominator 2 here multiplies the denominator 2 here. That becomes 1/4. Well, I mean 1/2 times 1/2. That's a half of a half. That's a quarter. So makes sense to me. Multiply that by sine of 2 times x. And that is equal to the derivative of cos squared x dx. And that would be our final answer. Ain't that neat? So let's see if the solution that we have here is agrees with us. Yep, we found the derivative of 1. That's just x on its own. The derivative of cos 2x. Yep, they found it to be 1/2 sine x. Oh, see, I made a rookie mistake. We need to include our constant of integration. So let's rewind here. Every time we integrate, we need to remember our constant of integration. And the reason why is, let's say we're taking an integral and then another integral, so a double integral. If we don't have the constant of integration, that means we will lose one of our terms, and that is absolutely not acceptable. So we always need a constant of integration. That's the plus c term every time we do an integral. So, don't be like me and forget that once, because you will have if your constant of integration is not present. So with the constant of integration, we can say that is the integral of cos squared x dx. Looks good. And I guess with their answer, they factored out 1/2 from here, but it really means the same thing. So verify solution. We know that the above solution is correct. Awesome. So we can move on to the next question that we have on the menu. Okay, so the next question that we have on the menu is, how do we solve the area of a circle? Let's see if I can draw a nice circle here. So if this is our circle, the area of the circle is just what is enclosed inside. Well, let's say right here, that's the center of our circle. To find the area of the circle, there's a couple ways that we could do this. Either that we know the diameter or we know the radius. And if you know one, you know the other. So we know that radius. Radius times 2 is equal to diameter. So I'll draw what the radius is. So this is the radius. Often we will call it just r. And the diameter, being twice that, is like this. And this is the diameter. The reason why both of them are important is, let's say you're trying to measure the radius of a hole in the ground. Well, it's very tough to know the exact center of the hole in the ground, so it's a lot easier in that type of scenario to use a diameter. But if you know one, you can easily find the other. So to find the area of this circle, we know that the area of circle, let's call that A. A for area. Makes sense to me. The area of a circle is pi times the radius squared, which is also pi times 1/2 the diameter squared, which is equal to pi times diameter over 4. Okay, so these are different ways that you can solve. You're going to want to use this one, diameter times pi divided by 4, or you can just do radius. Oh, that should be diameter squared. My bad. Diameter squared divided by 4 times pi, or you can just do pi times r squared. And if you didn't know, pi is a very, very special number in mathematics. Pi is a beautiful number. It is 3.1415, and it goes on and on and on. There's actually no final number of pi, but realistically, in most cases, you can get away with just using like 3.14. But if you want more precision, you can of course add more decimal points. It's just adding decimal points is not necessarily going to make you more and more precise after a certain point. Okay, so this is how you would calculate the area of a circle. Let's run an example. Let's say we found a cup, and the opening of the top of the cup is perfectly circular, and we found the diameter is equal to 3 centimeters. Now, a cup is a nice example because we can't necessarily measure the radius directly because, it's a hole in the cup. So, we can just get a ruler, go from end to end of the opening of the cup, and that will give us the diameter. So, if we want to find the area, we know that it's pi over 4 times diameter squared. If the diameter is 3 centimeters, remember always include your units when you can. It's important to have your units because let's say the diameter is 3 centimeters, so you just put 3, and then your area is like a number, and you don't have the units. Well, is that centimeters? Is that kilometers? Is that kilograms? We don't really know. So that's why it's always important to have your units. So I'm going to pull out my trusty calculator, and I will do pi divided by 4 times the radius, which is 3, and we're going to multiply by 3 again because that's what it means by squared. So we know that the area in this case is going to be 0.069 centimeters squared. Now, keep in mind, when we square this, we know that the centimeter, the unit, has to be squared as well. That's why we have square units, and like a square centimeter is a square that is 1 centimeter tall and 1 centimeter wide. Well, I guess it has to be 1 centimeter wide if it is a square after all. So that would be an example of how you can calculate the area of a circle. It's all coming full circle now. Great. So the above answer is great. So the above solution is correct. Cool. So we can move on to the next question. Okay, so our next question is, for what values of m does the graph of this function here, y equals 3x squared plus 7x plus m, have 2x intercepts? Okay, so let's write out that equation. Y equals 3x squared plus 7x plus m. And we want to know what is m so that there are 2x intercepts. So let's think about this graph visually for a moment. So we see that the leading coefficient on the x squared term is positive 3. That means that this is going to be a parabola, and what it's going to look like on the graph is kind of like a cup or a U shape. Okay, so the plus m term, since that's just like it's just m, it's just like a constant number. The higher it is, the farther up it goes, and the lower m is, maybe even a negative m, it will go farther down and farther down. Okay, so let's say we have the x-axis like this. If m is, let's call that x, and let's call that y. I don't necessarily know what this graph looks like, but it's just an approximation because I know it's going to be open, like cup shape or U-shaped instead of hill shaped. So if we have something like this, that means we have a big M. And if M is really big and it's above the X, that's going to be an issue because it doesn't intersect with the X-axis. Okay, now we have to think about another case. What happens when the base of the parabola is perfectly on the x-axis? That means there's only one x-intercept of the parabola. Well, the question is asking, when does it x-intercepts? So if it's this case and it's just like the lowest point of the parabola is touching x, that's not the quite right answer either. So we need to find what m is going to make the parabola like this, so that it has two x-intercepts. So this is probably going to be a low m value. So we're going to look for the m value that makes it such that the base of the parabola is lower than the x-axis. And to do that, we have a nice equation called the quadratic formula. Yeah, just going to verify something real quick. So the quadratic formula is very nice because it tells us the x-intercepts. And we know that the x-intercepts are going to be, based on the quadratic equation, minus b plus minus the square root of b squared minus 4ac. All of that is divided by 2a. So that's the formula that we're going to use to help us solve this. But let's figure out what a, b, and c are. So when we have a quadratic equation, it kind of looks like this. This is the general form. Y equals a x squared plus b x plus c. So from our equation up here, we can see that a, that's 3. B, that's 7. C, well, that's m. And we're going to need to keep it as like an unknown variable for now. But that is nothing to be concerned about. So let's sub those into the equation to see and see what happens. So x equals negative, well, sub in 7 for b, plus minus, under the root we have 7 squared minus 4 times 3 m, because c is m. All right, and all of this is divided by 2 times 3, which takes on the value of a. So let's clean this up a little bit. We have x equals negative 7 plus minus 49 minus 12 times m. And that's all divided by 6. We can rewrite this as negative 7 over 6 plus minus root 49 minus 12m over 6. Okay, now let's think about this for a second. Our x-intercepts for this graph, well, first let's consider the case where what's under this root is a negative number, meaning that m is very big. Then we have to take the square root of a negative number. Now that goes into complex numbers, but for the purposes of this question, we can just say the square root of negative is, let's just call that illegal. It's not completely illegal, but for the purpose of this question, it is. So really, the number of interest is what's under this root, and that's called the determinant. Now, let's think about this for a second. If the determinant is negative, well, that's illegal, and we should not even consider that case, and it doesn't. Actually, if it's negative, that means it doesn't intersect with x at all. And kind of like how we said before, since m basically moves the parabola up or down, if m is really big, or if as m gets bigger, the parabola gets farther and farther away from the horizontal x-axis, meaning that it's definitely not going to intersect with the x. Now, if the determinant is 0, we know that it is 7 over 6 plus minus 0 divided by 6. 0 divided by 6, that's still 0. So it's going to be 7 over 6 plus minus 0. So it's just 7 over 6. Well, that would be the case where we have a single x-intercept. So that's the middle case here. So we need what's under the determinant to be positive for this to be the case where we have two x-intercepts. Because if this is a positive number, that means we're going to have something here that's also a number. And then we're going to see that we have two answers. Negative 7 over 6 plus the number, and then negative 7 over 6 minus the number. And that would give us two x-intercepts. So basically, we just need to find out how can we make this underneath the determinant greater than 0. So let's actually write that as an inequality. So we know that 49 minus 12m has to be greater than 0. We can kind of, equalities are cool because they're pretty similar to equations. So let's bring the minus 12m to the other side. So we have 49. Basically, we're adding plus 12m to both sides. So that becomes plus 12m. And then we're going to divide both sides by 12. So m has to be smaller than 49 over 12. So let's actually try that. Maybe m is equal to something smaller than that. Let's say m is equal to, let's try with m equals 48 over 12. Because we know that 48 over 12 is going to be less than 49 over 12. So let's try the determinant. We know that it's 49 minus, what was it? It was 12 times m times 48 over 12. So we see how here, when we do the multiplication, 12 divided by 12, that basically they neutralize each other. 1. So we have 49 minus 48. And that is just the square root of 1. So if we sub that in here, with m equals 48 over 12, we will see that we get a positive number on top here, and then I'll actually write that out completely. So we had x equals negative 7 over 6. It was plus minus, I guess in this case it's root 1 over 6. As we calculated here, the determinant was 1 over 6. So that gives us two different values for x. So we're going to pull out my handy dandy calculator to help us figure out what that is. So we have negative 7 divide 6. And then let's do the case when it's plus 1 over 6. And that's just a negative 1. And then minus 1 divided by 6. And that is a negative 1.3 repeating, but that's also equal negative 4 over 3. So you see, when we tried this with a number, we know that m has to be smaller than this so that we can have a m has to be smaller than that so that we find two different roots or two different x-intercepts for the equation that we started off with, 3x to x squared plus 7x plus m. So this is our final answer. This is what m has to be smaller than for this equation to have two x-intercepts. Now, looking at the answer, they said x has to be smaller than negative 49 over 12. So I got to write in that this solution has a sign error. For this to have two x-intercepts, the m value must be less than 49 divided by 12. I'll specify that as positive because up here they said that it's negative. Proven by substituting in 48 divided by 12 for m. This gives us 2x or x-intercepts. So the solution is incorrect, unfortunately. But that's okay because we did find the correct solution. Awesome. Awesome. Okay. The next question that we have is, what is the identity property of addition? And this is actually shockingly simple. This just means that 0, the big O, 0 is a value representing nothing. What I mean by this is that typically when you're doing addition, like let's contextualize. I have 2 fingers up on this hand and 2 fingers up on this hand. How many fingers do I have in total? Well, we just do 2 plus 2, 4. Beautiful, right? Now let's say we had another thing that's like, okay, I have 2 fingers on this hand and no fingers on this hand. If we add them together, how many do we have? 2 still, because we added 0 to 2. So the identity property is a property of addition that says anything plus 0 equals anything. Or actually, I think it might be more appropriate to say something, because it's not like anything can be equal to anything else when you add it to 0. It's more like something specific plus 0 equals the same thing that it already was. Something plus 0 equals something. It really is that simple. So anytime you see something plus 0, just know you could remove the plus 0 and it would be just the same answer. So the above solution awesome. Okay, the next question that we have on the menu is, how do we evaluate this? Minus 2 to the power of 5. Well, it is tempting to say, that's just negative 2 times negative 2 times, that's just negative 2 times negative 2 times negative 2 times negative 2 times negative 2, 5 times. Yeah, it really isn't, unfortunately. So we have to remember something called bed mass. Or the order of operations. We know that the first place is brackets. Second is exponents. Tied for third place is division and multiplication. And tied for fourth place is addition and subtraction. Now, what this is saying is that we could rewrite this as, you see this negative sign? We would need brackets around this 2. To the power of 5. To make this like negative 2 times negative 2 times negative 2 times negative 2. So that would be negative 2 times negative 2 times negative 2 times negative 2 times negative 2. All right. What the top thing is saying is we could rewrite that as negative 1 multiplied by 2 to the power of 5. That's what essentially this thing is out here, the negative sign. What that means is that since we look at BEDMAS, exponents have to happen before you do the multiplication of the -1. So this is really -1 times +2 times +2 times +2 times +2 times +2, 2 to the power of 5. Pull out the calculator for that. I'm pretty sure it's 32. Would you look at that? I knew it. So this is really equal to -1 times 32, which is equal to -32. Now we see on the top, in this particular example, they are the same value. So like -2 times -2 times -2 times -2 times -2, that's that's still -32 because there's an odd number of negative signs, and every time we have a pair of negative signs multiplying together, they neutralize each other into a positive sign. So this is also -32. But please do not think that this is the rule always. If this was to the power of 4 instead of to the power of 5, these would be different. That would be a positive number. This would be a positive number, and this would be a negative number. So I'll actually write that as an example. Let's say we have -2 to the power of 2 versus -2 in brackets to the power of 2. This is equal to -4 because it is equal to -1 times 2 times 2 is not the same. This is -2 times -2, and that's +4. You see how these are not equal anymore? The solution that we have here, unfortunately, is not correct because BEDMAS is ignored. So unfortunately, I do have to mark this question as incorrect. The above solution is incorrect. So BEDMAS is ignored as brackets were added when they really should not have been. -2 to the power of 5 is really equal to -1 times 2 to the power of 5. While the result is the same for this example, the result would not be the same for cases where the power is an even number. So be very careful about BEDMAS. So gotta mark this as incorrect, but that's cool because even Isaac Newton made mistakes. Okay, now let's take a look at the next question that we have. The question is asking, which of the following could be the equation of the function? And they give us some options here. So let's take a look at the graph and let's look at some points of interest. So we see when x is equal to 0 on the y-axis, the y is equal to what looks like -1.5. So let's write this as a point like this, xy. Whoops. xy. One of our points of interest is 0 and -1.5. Let's find another point of interest. When x is equal to pi, we have y also equal to negative 1.5. Now with these 2 points of interest, we can kind of sub these into the other equations and we can see who works and who doesn't work. Okay, but first let's take a moment to think about this. So we see all of our options are cosine functions and they all have a coefficient of 0.5. So we can't disqualify anyone based on that, but we can look at the end. See how this is like minus 2 plus 2, minus 2 plus 2? Typically, a cos graph looks like this. Or actually, I can even pull up my Desmos, my graph. Let's do cos x. Typically, it looks like this. It will start at 1, and then when x is equal to 0, y will be 1, and then, you know, it goes down and it waves around like that. This is not at 1. So this is below 1. So if we were adding, we would be moving the entire wave upwards. So we need a minus term for it to move downwards. So A and C can be disqualified quickly just off the fact that they have plus terms at the end. So we know that not A, not C. So we have to check between B and D who works out. Well, we can just we can sub in our points of interest and we can hopefully find out. So let's try with B first. So B is y equals 0.5 cos times 4 times x plus pi over 2 minus 2. So let's sub in our point of interest, pi and negative 1.5 for y. So we have negative 1.5 equals 0.5 cos 4 times pi plus pi over 2 minus 2. Let's pull out my handy dandy calculator to calculate the right side of this equation. So we have pi plus pi divided by 2. That guy is multiplied by 4. And we're going to need to take the cosine of that. So I have to set my cal to radians. Do that super fast. So the cosine of 4 times, I guess 3 pi over 2 is 1 times 0.5 is 2. And then, I mean, it's not 2, that's a 0.5. Minus 2 is negative 1.5. So we're probably good on that, but that doesn't necessarily mean that we can disqualify it. Actually, instead of subbing things in, we should see that, you see this term? We have like a 4x term. Okay, so it turns out for both B and D, if we sub in our points of interest that we got off the graph here, we will see that they both actually work. Now, a thing to note is that typically one period of a cos, meaning like it goes all the way down and all the way back up, is going to be 2 pi. But here, it goes up and down and up and down. So in a single pi, there are 2 whole periods. So that means it is going 4 times faster than just regular cos. So that means that we have, it's going to be the thing that's multiplied by 4 instead. Because we know that it is going 4 times more frequently than it would be regularly. Normally, you would only have a half period at pi. You see here, pi is halfway through the entire wave cycle, but a full wave cycle is 2 pi. Now in 1 pi, so that's half the distance, we have 2 full waves. If we had 2 pi, there would be 4 full waves. So this is going 4 times more frequently than it should be, which means that what's inside of the multiplication here, it should correspond to multiplying by 4. So let's actually stick this equation into Desmos and see if it lines up. So it was 0.5 times cos, it was 4x. You see, if we multiply by 4, how much more frequent the graph gets. It was 4, and it was x plus pi over, I think it was pi over 2. Yeah, pi over 2. Oops, pi over 2. Get that bracket in there, and then minus 2. So our points of interest, are they here? Pi and negative 0.5, 0. And look, it matches with our points of interest. We have a peak at 0, a peak there, and a peak at pi, like one peak in between pi and 0. So that matches up. Let's see D. If we plot D, we should see that this is definitely not the same. So I'll plot that. 0.5 cos, 0.5 times cos, 2 times x plus, I think it was x plus pi, x minus pi, minus 2. Hey, well, you see for D, when we have the factor of 2 out here, it's not frequent enough. So we have to disqualify D on that. Because it's going 4 times more frequently than it normally is, we keep in mind the 4. So, yep, it's the term that's multiplied by 4, so that's good. And since we're multiplying by 4, it's going 4 times more frequent, meaning that it's compressed by a factor of 4. And we sub in the values. So the choice is B, and there's a big detailed explanation on that, with some more, I guess, formal mathematics about like how you can change the phase and or the compression term. And here, multiplying by 4 compresses the entire graph to be 4 times more frequent than it is regularly with just like cos x. So the above solution is correct. Awesome. So the next question that we have on the menu today is find the derivative of 5 to the power of x. So d over dx, 5 to the power of x. We know that The general formula for the derivative of something, let's call that base to the power of x, is equal to the natural logarithm of the base multiplied by base to the x. Okay, so let's do this when base is equal to 5. This is one of those equations that you're probably going to need to memorize, because you will likely see a couple, like this is a moderately, or it's a pretty common derivative that you'll need to know. So keep that in mind. So we know that we have to multiply it by the natural logarithm of 5 multiplied by, well, 5 to the power of x. And what is the natural logarithm of 5? Pulling out my calculator to find out. Natural log of 5, 1.6094. So, or this is about equal to, because typically you want to leave it at like this so that it's more exact, but the approximated answer is 1.6094 multiplied by 5 to the power of x, which pretty much means the tangent line so 5 to the x is an exponential graph. So it's gonna start and it's gonna grow, and then every time it grows more and more. So that just means like the tangent line is gonna be steeper than its actual value. Cool. And yep, so I guess they have it. They just wrote it in the other way around, but it's really the same, because multiplication, you can reverse the order and everything's the same. So for this question, the above answer is correct. Cool. So the next question that we have is, what is the value of x? And we have a little triangle here, and we only know one of the angles inside of here. So I'll draw a little triangle to okay. Okay, never mind. I'll just draw that by hand, because that is not the same direction, and it's also a right angle, which is not, even though it's close. So that's x. That's what we're trying to find. We know that that is 95 degrees, and we know that this is 60 degrees. Okay, so what is some base knowledge about angles and triangles that we have to know? We have to know, this is an extremely important rule. The sum of all angles inside a triangle is 180 degrees. Awesome. And the second thing that we know is, when we have a straight line and a situation like this, let's say we have angle A, and here we have angle B. We know that A plus B is equal to 180 degrees, because we have a straight line on the base here. And we know 180 degrees, well, that's a complete like U-turn flip, 180 degree flip. Like, we've probably heard that in I guess contemporary language. So, hey, wait a minute. Let's say we have B, and let's say A is equal to 95 degrees. We could solve for B. So we can do B is equal to 180 degrees minus A. just subtracting a from both sides of this equation. So if b is 100 degrees minus a, 180 degrees minus a, and a is equal to 95 degrees, we know that b must be 180 degrees minus 95 degrees. And with some quick math, that is 85 degrees. So that is 85 degrees. Oh, and remember when we said the sum of all angles inside a triangle is 180? So we know that would just be x plus 60 degrees plus 85 degrees is equal to 180. Let's write that out. 180 degrees is equal to x plus 60 degrees plus 85 degrees. With some quick math, let's subtract 60 from both sides, and we're going to subtract 85 from both sides. So that's really just like 180 minus 60 degrees minus 85 degrees. And that just leaves us with x. So 180 minus 60 minus 85, what would that be? 35 degrees. Does that make sense? Seems about right. 35 plus 85 plus 60, is that 180? Yes, it is. So it keeps the rule that all angles inside a triangle is 180. And we know that if we have a straight line and you know the angle that something makes with the straight line, you can find out the other thing just because you know that 180 degrees is the total angle of a straight line. Something like this. Even though it looks like just a straight line, imagine those are like here we have a ruler and pencil. Like now they're about 90 degrees, now they're about 180 degrees separated. Now they're 0 degrees separated. So yeah, keep that in mind. Cool, so there's multiple choice question, and we have b is equal to 35 degrees. It's got to be b. Got to be b. Yep, answer 35b. Guess they have a more formal definition with like the theorems, but knowing the theorems by name is less important than knowing how to use the theorem. So we know that the angle inside is always going to be angles. The sum of all angles inside a triangle is 180. On a straight line, those two angles, if you know one, you can find the other by subtracting, or 180 minus the one you know. But I guess they just kind of compress that into a different theorem, which also works because we come to the same result, but in my opinion this way was a little bit easier because we just need two very basic rules. So the above solution is correct. Awesome. Okay, now let's take a look at the next question on the menu. So we have the derivative, so that's d over dx, of x times natural logarithm of x. Now, okay, we got to look closely here. We have two functions here. And when we take the derivative of one function multiplied with another function, we have to use something that's called the product rule. And the product rule says that if we're taking the derivative of something, a function, multiplied with another function, the first function we'll call it f of x, second function we'll call it g of x, we know that the product rule states that the derivative of their product is the derivative of the first one multiplied with the normal second one plus the normal first one multiplied with the derivative of the second one. You kind of see how these two are like not exactly twins, but they're like vice versa of each other, more like cousins. So we can just use this rule and input these for f and g of x, because this is our general equation, and we can use our general equation to help us handle a specific case like this. So in this case, f of x is going to be just x itself, and g of x is going to be a natural logarithm of x. So let's a derivative of f of x. So what's f prime of x? F prime of x is the derivative d over dx of simply x itself, and that is a nice easy 1. Because x is just a diagonal line along 45 degrees. The tangent of that has a slope of 1 always. It's just a straight line. Nice. Okay, now what about the derivative of g of x, which is d over dx of a natural logarithm of x? This is 1 divided by x. And this is an important derivative that you definitely need to know, because you will see this a lot. Okay, so now that we know our f of x, we know our g of x, we know the derivatives of both of them, let's input them into our little equation here, or our general formula for the product rule. So we got d over dx of x multiplied with a natural logarithm of x is equal to derivative of the first one, so that's just x. So that is 1 well, let's not use x because that will get confused with the variable x for multiply. 1 multiplied with the normal second one, g of x. So that's just a natural logarithm of x. Plus the normal first one, so that's regular x, just x. Multiplied by the derivative of g of x. So that's 1 divided by x. Okay, we can make this a little bit simpler. So 1 times ln of x, that's just natural logarithm of x. Sometimes people call it ln, so stay ready for that. And what's x divided by x? It's 1. That's the 1. Exactly. So we know that our derivative of x ln x is ln of x plus 1. And we figured that out with the power of the chain rule. I mean, not the chain rule, the product rule. Okay, and here in the answers, they had the product rule, and they came to the same conclusion, but in a different order, but it's the same thing. So the above solution is good. That is great. Cool. So let's submit that. Okay, now the question is, which algebraic expression of these 4 is a polynomial? Let's first talk about what even is a polynomial. A polynomial is an equation of terms where you have x to the power of n with some type of like coefficient. Let's call that c of I, because you're going to have different coefficients for each one of your terms. Let's actually write that on a different line so it's just a little bit clearer. Where you have like a constant or a coefficient multiplied by x to the power of some n, and you add them all up this sigma represents a summation. And you cannot have n has to be greater than or equal to 0, meaning that you're not allowed to have negative powers for n in your polynomial. That's going to be the main thing that we can use to disqualify some of these things in here. Oh, and also n is an element of the integers, meaning that fractional okay, this z is often used in mathematics to represent integers. That just means like we can't have like x to the power of 0.221, something like that. You have to have like regular whole non-decimal numbers in the power. Okay, so let's see what we can let's take a look at our options and see what we can disqualify here. So the first one, so A, is 4x squared, looks good so far, minus 3x, that's x to the power of 1, plus 2 divided by x. Now 2 divided by x is equal to 2 times x to the power of negative 1. Those two are equal. So because we have a negative 1 here, and the rule for polynomials is that you strictly have powers that are positive and non-fractional, you know that this has to be disqualified. So A, no. It is not A. Okay, now let's check for B. B, here we have negative 6 x to the power of 3 plus x squared minus the root of 5. Hey, all of these powers are positive. None of them are negative. None of them have fractions. So B, so far, passes the test. Now, don't get confused here, because you do see like a root, and roots do correspond to like the root of 5 is equal to 5 to the power of 1 over 2. But that's okay because the power here is not attached to an x. So all the x's have powers that are positive whole numbers. So B passes the test. Now let's take a look at C. So C, we have 8x squared plus the root of x. And like I mentioned here, the square root is equivalent to a power of the power 1/2. This we have 8 times x to the power of 2 plus x to the power of 1/2. Now see, that power to the 1/2, that breaks the rule. That is 0.5. So that breaks the polynomial rule because all that powers on x have to be positive whole numbers. So that breaks the rule. It's not C. But I can see that it's not C. You see? Okay, so let's take a look at D. Oh, and D is another one of those situations where we have negative 2x to the power of 4 plus 3 over 2 times x, which is really, when you have an x downstairs on the fraction, that just means like its regular power is actually negative when you bring it upstairs. So let's bring the x from the downstairs denominator of the function and we can bring it upstairs. So we're going to have negative 2x to the power of 4 minus 3 over 2 x to the negative 1. Uh-oh, negative power. That's a rule breaker, so it's not D. So the only thing that didn't break the rule, that's B. And I guess it wasn't entirely necessary for us to prove that C and D are rule breakers, but you know, if we see that that A, C, and D are rule breakers and B is the only one that's not a rule breaker, that means the answer, that's got to be B. Big B. And yep, they say B is the only one that is a polynomial, so we can confirm that this question is good. Okay, and I guess that that was the last question. Time flies when you're having fun, as the old saying goes. Okay,